Buenos días a todas y todos. Mi nombre es Ania León y es, la verdad, una gran felicidad seguir con este proyecto en el cual estamos promoviendo la cultura positiva de la inocuidad de los alimentos en toda Latinoamérica. Y hoy tenemos una vez más a un profesor que realmente es un honor para nosotros contar con su participación, del profesor Bala, que va a estar dándonos nuestra sesión del día de hoy, hablando sobre innovación en el procesamiento de alimentos para lograr pues evidentemente una alimentación futura mucho más segura y mucho más saludable. Además, contamos también con la participación del profesor Oscar Acosta, quien será el líder de la sesión, pues en esto, pues un tema tan complejo, pues va a estar con nosotros. Así que bienvenido, profesor Oscar. Please welcome Professor Bala. Thank you very much for joining us, and thank you, Professor, for being the host of Professor Bala. We really appreciate it.
Okay.
Siempre hacemos una presentación de lo que es ILSI. Recuerden que somos una organización global de científicos que actuamos de manera conjunta en un ambiente neutral del más alto nivel de integridad científica y que nuestro objetivo pues es proveer ciencia con el objetivo de impactar la salud pública, el bienestar y el desarrollo sostenible. Somos una organización tripartita que trabajamos de manera conjunta, los industriales, los académicos y los gobiernos, para lograr un impacto más efectivo y más eficiente también. Recuerden que pueden visitar nuestra página web, que es ilsimesoamerica.org, para conocer más sobre nosotros. Y siempre hacemos esta declaración de exención de responsabilidad de manera tal que todo lo que nuestros invitados especiales pues nos ofrecen en sus conferencias lo hacen en nombre suyo personal y no en el nombre de ILSI como tal. Además de que siempre actúan de manera voluntaria, con total libertad de hacer sus presentaciones, y tampoco han recibido remuneración por su participación. Así que siempre les agradecemos a todos ellos por estar con nosotros y brindarnos este tiempo de preparación de presentación, y además el tiempo de estar con nosotros y con todos ustedes para brindarnos su ciencia, su experiencia y sus conocimientos. Así que por eso le damos hoy la bienvenida. Professor Bala, thank you very much again. And Professor Oscar, the floor is yours to presenting Dr. Bala. Thank you.
Thank you very much. Muchas gracias, Ania, y buenos días a todas las personas que están actualmente con nosotros en este webinar tan relevante para el sector académico, el sector industrial. Tenemos un invitado de lujo el día de hoy, el doctor Bala Subramaniam de la Universidad de Ohio State. Quisiera agradecerles a todos su asistencia y en particular a Ania por la organización y demás personal de ILSI de este evento. Si ustedes están de acuerdo, voy a proceder por un asunto de respeto a presentar al doctor Bala Subramaniam en inglés y luego le daré la opción también a él de iniciar la disertación. Las preguntas las podríamos tomar al final del evento, las pueden hacer por el chat en el transcurso de la presentación, si fuera posible, y yo con muchísimo gusto me encargaré de hacérselas llegar al doctor Bala Subramaniam al final de la actividad. Lo pueden hacer en inglés también directamente, pero en tema de orden preferiría que me las indiquen en el chat y yo las transmito directamente al expositor. Okay, so good morning, everyone. Dr. Bala Subramaniam is with the Ohio State University College of Food, Agricultural, and Environmental Sciences, Department of Food Science and Technology, Food, Agricultural, and Biological Engineering. His research and industrial outreach efforts contribute to the development of sustainable food processing and sanitation technologies to ensure microbial safety and preserve product quality and nutrition. Dr. Bala teaches graduate and undergraduate courses in unit operations in food processing and engineering and co-teaches a class on food process sustainability. His research contributions have been recognized by his peers. He was the recipient of the 2021 Research and Development Award from the Institute of Food Technologists, and he has been elected a fellow of IFT, of the International Union of Food Science and Technologies, and the Indian Society of Agricultural Engineers. He is currently serving as the editor-in-chief of Wiley's Journal of Food Processing Engineering. So Dr. Bala Subramaniam, Bala, thank you so much for being with us today. It's an honor to be with you, sir. And if you are okay with the introduction and you can start, I can take questions as soon as they reach me in the chat, and I can translate them for you if that's okay with you, sir. So thanks so much, sure. And the floor is yours. Thank you.
Okay, Good morning, everyone. First of all, I would like to thank the organizers for this opportunity to share some of our research. And I'm going to make a presentation, but feel free to make it interactive, ask questions. I can stop by and then answer those questions before proceeding. The next slide, please. A brief introduction about me, or like I think, thank you for the good introduction. So I'm going to provide a brief overview. So this is a basic introduction about me. I have done bachelor's degree from India in agriculture engineering, master's from Asian Institute of Technology in Thailand, PhD from Ohio State University, and I did my postdoctoral research at University of Georgia, and I was also with the National Center for Food Safety and Technology and FDA consortium in Chicago before joining Ohio State in 2002. Next slide, please. So in this presentation, I divided this into 3 modules. The first module, I'm going to focus on some of the driving forces. What is the motivation for developing sustainable food processing technologies today, why there's a lot of interest. The second, I'm going to provide a overview of some of the key thermal and non-thermal processing technologies. Then I'm going to consider what are the factors you need to consider for technology development and implementation. Next slide, please. So the model 1 focus on driving forces. Broadly speaking, there are 3 factors. I think one is the interest in sustainability. The second is the nutrient and health, because there's a lot of interest in health, particularly with the COVID. And I think both these efforts are driven by consumers, and food industry as a consumer-driven industry is responding to these needs from both sustainability and nutrients and health. Next slide, please. So if you look at historically, food manufacturing industry is probably one of the very safest. In particularly in the U.S., the people enjoy safest, more abundant, diverse, affordable food supply. And the industry probably started in the 1900s with the formation of the Food and Drug Act. And then since then, it is kind of adapting various consumer trends. And in the US, it's one of the top 10 manufacturing sectors. And I think if you look at globally, it is probably similar because all of us are consumers and we eat 3 times at minimum so we can be able to touch with the food. So it's kind of very related to all of us. And it's also economically very important. In the US, there's a $2.12 trillion is associated with the foods, and it employs a lot of people, 1.7 million people. And wide range of food categories are processed by this industry, ranging from canning, pasteurization, frozen beverages, and so on. Next slide, please. So there's a lot of things going on, and then I think people are happy and we are proud we are one of the safest industry. However, there has been problems start associating, particularly in the last 10, 20 years. There's an emerging trend showing that the chronic diseases, lifestyle diseases such as diabetics, obesity, hypertension, cancer, and that's related to the processed food. For example, some of the synthetic additives can affect the human health, and you also have a lot of trends associated with that. As a result, the consumers begin to question the safety of the processed food. Next slide, please. So, for example, you can probably see in your regular newspapers people reporting how food additives link to health issues, and people start responding, the regulators start responding, they start banning the food additives and so on, and then the consumers worried the safety of processed food, which was considered safe for quite some time. Next slide, please. As a result, the consumers still want to consume processed food because they realize this is the best vehicle they can use to consume, but they want the processed food to be safe, and it also has a lot of the health promoting nutrients preserved, and there's an interest in high protein diet, and they also want to reduce the sugar, salt in processed food, and there's an interest in sustainability and waste reduction. So, and I think as a result, the consumers have interest in clean label processed food, which are free from synthetic ingredients. Next slide, please. You may ask, what is a clean label? I think there is no formal definition for clean label, but generally speaking, some of the questions help to explain what is clean label. Is a clean label processed food help to maintain natural freshness and taste? And is it formulated similar to a home prepared meal? And can this use more natural ingredients than without using some of the synthetic ingredients and chemicals? While doing so, they also want to make sure that it has a proper shelf life and extend the uh, food safety benefits. And is it again environmentally sustainable? Next slide, please. From an environmental sustainability, um, again, food manufacturing industry, particularly in the US, is one of the top 5 consumer of fuel and power. It generates a lot of carbon emission. So, for example, it's fourth highest in the U.S. manufacturers in terms of carbon dioxide emission. It also uses a lot of water for various food process operations. Another thing, at least in the US, in many countries, is that 1/3 of the food is wasted by the consumers. In many developing countries, 1/3 of the food is lost during the post-harvest losses. So nevertheless, there's a loss of food occurs. Now, with the world population expected to increase quite a bit by 2050, there's an urgent need for food processing technologies so that we can feed comfortably all the growing population, yet it also make it healthy. So I think that's basically one of our challenges facing food scientists and engineers. Next slide, please. So as a result, there's a growing interest to develop next generation of food processing, packaging, and ingredient technologies to ensure safe and wholesome processed food with consumer desired attributes. Next slide, please. So when you develop a food processing technology for the next generation, it's not just a simple factor you can decide and then make a determination. Historically, we develop food processing technology based on food safety. I think still that's a very important. But in addition to that, now you also need to make sure it is nutrient or preserved so that it has a health promoting properties. And it also need to have a sustainability so that it kind of meets reduce the environmental impact. And from a food manufacturing point of view, they need to have proper techno-economic justification because these are done by manufacturing industry who are private industry who need to make money to sustain the business. So the processing technology needs to be cost effective. And COVID demonstrated that it is important to maintain a good supply chain So they need to consider these is also adequate for supply chain. Ultimately, whenever you develop a technology, the consumer doesn't know the technology. They accept only the food product. So they need to make sure they accept the food product. Good example is food radiation. Food radiation as a technology developed a long time ago. However, with the consumer hesitant to accept radiation technology, never been commercially successful. So when we develop new technology, it has to be accepted by consumers. Next slide, please. So in this presentation, next module, I'm going to talk about some of the advanced thermal and non-thermal processing technologies. Next slide, please. So one of the limitations of the conventional processing technology is the slow conduction and convection heating. Like a lot of the foods are pasteurized or commercially sterilized or canning with the heat treatment. And during heat treatment, the process is quite effective, microbiologically safe, but conduction, convection heat treatment is very slow. So one of the approaches people tried initially is the advanced thermal process, which volumetrically heat the whole mass. So for example, if you have a chicken, rather than heating the outer portion of the chicken and then the heat transfer internally within the chicken, you can microwave the chicken so that the entire mass of the chicken can be heated. And similarly, you have only heating, other technology, and so on. And here, still, we are using heat as the primary mode of destruction for bacteria. And the criteria for pasteurization and sterilization, they are very similar to conventionally processed food. Next slide, please. So for example, heating is a technology where you can pass electricity through the food so that you can able to heat the food quite rapidly. It's a volumetric heating, and this has been adapted for viscous and particulate foods. And here, the heat is passing through the electricity, and that means the electrical conductivity of the food material is important so that it can ensure uniform heating. Liquid egg, pet products, whole foods. So these are some examples of commercial products available in the market. However, this is still a heat treatment. You can able to rapidly heat, but when it cooling down, it's going to take time to cool down. So there may be some degradation of the product can happen. Next slide, please. Microwave heating is basically here you use microwave to heat the food, and basically when you expose the food with microwave, the molecule oscillate at frequency, causing internal heat generation due to dielectric and ionic properties. And the mechanism of inactivation is still thermal. And here you can able to quickly turn on and off the microwave so that you can able to control the heating rate. Now, in the US, microwave is become commercially adapted. It's called microwave assisted thermal sterilization MATS process. So, for example, like salmon fillets and sweet potato puree are some of the products kind of FDA issued no objection to commercially process them. Next slide, please. So this is just an example for a microwave-assisted thermal sterilization unit. You package your product and then place inside a chamber and then expose to the microwave that's shown in that blue box, blue slide. And the microwave is kind of delivered on the conveyor mechanism and it heats the product. And since you are sending your packaged pouch in a water, the microwave heat both the product as well as the water so that you can ensure uniform heating of the product. Next slide, please. This is a continuous microwave sterilization unit. You can be able to pump, for example, a soup-like material through a system, and the microwaves are delivered inside the chamber. So it's kind of shown in the right side here, and so that way, like you can able to process the product, and then you can able to do it. So the previous slide is a batch system, and that was developed at Washington State University. This current slide, continuous microwave sterilization, is developed at the North Carolina State University. Next slide, please. Now we are coming to next category of non-thermal technologies. These are non-thermal technologies. The reason is they do not use heat as a mechanism for killing the microorganism. They use lethal agent other than heat to kill the microorganisms. So a classical example is radiation, which uses ionization radiation. Because of the consumer acceptance issue, it's never been commercially successful in the North American market. The next category of products are called high pressure processing, which use extreme pressures, ultrasound, supercritical CO2, pulse electric field processing, UV processing, and then there are several gas-based technologies, ozone, chlorine dioxide, coal plasma, and so on. So these technologies use a lethal agent to kill the bacteria without heat, and they have variable efficacy in terms of killing the enzymes or inactivating the enzyme. Next slide, please. So these non-thermal technologies make the food safe by killing the bacteria and spoilage organism. And since they do not employ heat, they reduce the thermal exposure. Since heat is the primary reason why nutrients are destroyed, you'll have a less impact on the nutrients, and you can able to formulate novel products. Like heat processing, they can extend the shelf life of the food, and many of the non-thermal technologies, they can reduce the use of synthetic ingredients and preservatives. So, for example, a lot of the high pressure processed products have the opportunity to make clean label products. Since these non-thermal technologies, these are all modern technologies, they use primarily the electricity, they do not use the steam, and as a result, they tend to be environmentally friendly. They also have less use of water, and thereby they can able to reduce water use. And since they have longer shelf life, they can also reduce the food waste. And the consumers also seems to be readily accept many of these non-thermal technologies, and as a result, there's a lot of opportunity for creating next generation of new products which is previously didn't exist. Next slide, please. So we kind of talked about food radiation. So food radiation use ionization radiation, pasteurization and sterilization effects are possible. It's scientifically safe, but consumer acceptance is probably limited acceptance of this product. In addition, in the US, the regulators require packaging go through pre-market approval. So there's a packaging material qualification, and then the package needs to be labeled with the Idora symbol. As a result, I think it's kind of a very difficulty in getting acceptance. Next slide, please. High pressure processing, basically you employ pressure in the range of 600 megapascal or 87,000 pounds per square inch pressure. If you ever go to the deepest part of ocean, like Marina Trench, it's 5 times greater pressure. And one of the interesting thing is the high pressure processing, even though we call today as a new technology, the original concept was demonstrated in 1890 there's a scientist by name Haidt. He demonstrated in ag experiment station in Virginia Tech that you can able to pasteurize milk with application of pressure. However, the technology never find commercial traction until 1980, and Japan looked at this research and then they commercialized it. Then US followed that, and then it became commercial in 1997. It has a very short treatment time, 30 seconds to 2 minutes, and it preserves the nutrients. It doesn't require use of preservatives and ingredients, and it helps to satisfy consumer demand for clean label products. Next slide, please. So the next couple of slides, I'm just going to show you some of the successful high pressure process product. One of them is a deli meat, and in the 1990s and 2000, there were a lot of outbreaks with meat. The USDA Food Safety Inspection Service indicated that you want to have zero tolerance for listeria in processed meat. And high pressure happened to satisfy that opportunity, and it can help to inactivate listeria, salmonella, campylobacter, and many other bacteria. And you can able to extend the shelf life, and you can able to create a more natural product. A lot of times in the processed meat, you need to use the nitrate to make the product stable. With high pressure processing, it eliminates that need. As a result, it becomes more clean label product. So you can able to adapt variety of different products in the meat sector. Next slide, please. Seafood is another application. At about the same time, the seafood industry faced outbreaks with Vibrio bacteria, and with a consumer concern, I think the industry is looking for ways to make the seafood safe. When you heat the seafood, it kind of make the meat not appealing. So the industry was looking in non-thermal ways to make the food safe, and they found high pressure able to accomplish. One of the interesting things happened, in addition to inactivating Vibrio, they can also able to show that the shell and the muscle, they have different compressibility properties. As a result, they can able to remove the muscle from the shell, and this process is called shucking. And with the high pressure processing, shucking became a major labor saving opportunity. In addition, you can create novel infusion. So, for example, you suspend your product, for example, lobster or oyster in a lemon juice. You can infuse lemon into your product, creating new product category opportunities as well. So, there's a lot of innovations can possible with this type of technology beyond food safety. Next slide, please. With the consumer interest in health and wellness, the beverage industry started introducing a lot of products. For example, Starbucks introduced many juices and smoothies, and many other companies introduced coffee under the liquid beverages. And these beverages use high pressure and help to preserve the nutrients present in this, and also extend the shelf life. Next slide, please. The next slide. So the high pressure processing, like thermal processing, is an versatile technology. It can be used for a wide range of categories. We talked about meat, poultry, and we talked about seafood. It's also applied in pet food, baby food, dairy, juice and beverages, ready-to-eat meals, and so on. So these various categories of the products are introduced. It's worth point out that while internationally the dairy products, for example, high pressure pasteurized milk is commercialized in Australia. In the US, because of the regulations, um, what they call pasteurized milk ordinance, it's not yet commercially possible, but it's just going to be introduced in a matter of time. Next slide, please. Other technology with the success of high pressure processing now being developed, including the at Ohio State, is called ultra shear technology. Success of beverages with high pressure processing led to the development of ultra shear technology. Because high pressure processing is batch, whereas beverage manufacturer, they want more continuous methods of processing. So as a result, this technology is developed where you introduce the raw product subject to pressure treatment, and then you discharge the product through a shear valve, and then you collect the product in a treated liquid. Next slide will probably going to show you a better outlook of that picture. So here you have a product tank and you have a raw beverage, and then you are pumping that product tank and then introduce the product into the two pressure chambers. And the product is flowing inside the pressure chamber through a flexible tubing, and you have two of them. And then you have a pressure pump which introduces water as the pressure transfer fluid, and that is going in the annular space between the pressure chamber and the product. And then after reaching the target pressure, it's discharged through a shear valve. So one end is going to be, say, 400 megapascal. At the other end is going to be atmospheric pressure, and there's going to be some temperature increase during processing. Then you're going to send it through coating tube, and then you can cool it down and then aseptically package it. So this is a technology which combine both non-thermal aspects of high pressure processing and then thermal aspects of the aseptic processing. So it's a hybrid technology. Next slide, please. So this is a video. I think this is being a slide. I think we'll probably skip the video, but I think I can share this video later on via slide. But it's just to show you the operations of the pilot scale ultra shear technology. Next slide, please. So the application of high pressure processing with ultra shear technology, it can use for pasteurization and sterilization of various beverages. In addition to that, when you send the beverage through the shear valve, it's going to modify the structure, it's improve the viscosity, it blends the various ingredients and reduce the particle size and then emulsify. So as a result, you can be able to formulate some novel products. You can create a high-fat product from a reduced fat ingredients without adding any thickness. And you can create a nano emulsions for applications in food processing, agriculture, cosmetics, and medicine. You can also use this as extraction technology for extracting bioactive compounds and various compounds with reduced processing time and use of chemical solvents. Next slide, please. Pulsed electric field processing is a technology which uses very high voltage instead of pressure. This uses 30 to 50,000 volt per centimeter electricity discharge every nanosecond, so that you can be able to inactivate microorganisms. It's primarily useful for liquid foods, and you can be able to pasteurize, which is probably widely commercialized. And sterilization application is still being developed, and it has a variable effect on enzymes. Next slide, please. So pulse electric field processing um, initially was developed as a food safety technology. However, the commercial application today is not food safety, but for quality purpose. So for example, there are companies use this in the US and Europe and elsewhere for making French fries. And by treating potato with French before making French fry, it helped to reduce the oil absorption. The same way they can use this for treating grapes so that you can have a wine with less sulfite for stabilization purpose. It's also used for preserving fruit juices, liquid egg, and many other similar beverage products. Next slide, please. Cold plasma is another new processing technology. Many of the technologies I talked earlier, like high pressure PEF, they cannot be used with fresh produce, like, for example, leafy greens and things like that. And when you have some of the intermediate moisture content type products, like nuts and things like that, they cannot be used. So what cold plasma is, basically, you create a plasma. It's like a arc created from the by passing electricity through a carrier gas such as air, oxygen, and nitrogen, and it has number of uh, complicated mechanisms, but essentially it's a UV light with some ozone and reactive chemical species, and it has a potential applications in meat, poultry, fruits, and vegetable products. Most of the research done with cold plasma is primarily done at a lab scale. Now there are some limited pilot scale experiments are available, and the science behind the mechanism of cold plasma is still evolving, and there's also need for scaling up the equipment. So comparatively, it's one of the less developed non-thermal processing technology, but I think a lot of promising future. Next slide, please. The next several slides, we are going to consider how do you develop non-thermal technologies and industrially implement. Next slide, please. One of the first things you need to consider is how uniform your technology application is. So for example, when you think about high pressure, is the pressure application is uniform throughout the volume. And if you look at thermal processing, there's a non-uniform temperature distribution that lead to poor conduction convection treatment. But in the case of pressure, whether you use a small bottle or you use a large chamber, the application pressure is quite uniform. You have to think about the same thing for various things, whether you talk about UV, you talk about pulse electric field processing or pulse light or ozone and so on. So for example, if you think about some of the light-based technologies like pulse light, light by nature can create shadow. So when there's a light, you can have a uniform application. But when there is a shadow, because of the irregular geometry of the food or some other reason, under those conditions, if there's a microbes present, they will survive and that can cause an outbreak. So you need to understand, so you need to mathematically model to identify the least treated zone within your process. You also need to think about some of the engineering properties associated with your technology. So for example, when you want to commercially sterilize pressure thermal sterilization, you need to know the thermal conductivity, specific heat density, and heat of compression as a function of both pressure and temperature so that you can utilize them in the mathematical modeling. When you use the light-based technologies, you need to look at surface reflectivity, the distance between the light source and the food, the intensity of the treatment, and so on. When you look at pulse electric field technology, you need to think about the electric field, electrode design, electrical conductivity of the food material, the duration of the pulse, frequency, waveform, and number of pulses, and so on. So each technology has a unique set of properties, and you need to make sure that ultimately the treatment is applied uniform so that you can have a safe product. Next slide, please. These technologies also have a unique mode of action. So, for example, if you look at the high pressure processing, it uses isostatic uniform application of pressure, and the pressure going to denature some of the cell membranes and then modify the structure, thereby make it effective. Whereas in the case of pulse electric field processing, it uses a concept called electroporation. It's going to put a hole with application of pulses, and that leads to the cell death. In the case of ultrasound, it uses cavitation, and it increases the diffusion of water and leads to cell death. And same way, cold plasma and microwave each use their own set of things. So when you look at a technology to commercialize, you need to understand what is the underlying physics with that technology, how that affects the food safety, how that affects the nutrients. Then you kind of make a holistic determination in identifying the process conditions. Next slide, please. So in the case of high pressure processing, you apply pressure, develop the pressure, and keep it for a certain time, and then depressurize it. During that time, there's an increase in temperature, and depending on the equipment, the temperature can be stable, or you maybe lose the temperature during pressure holding time. And when you release the pressure, the temperature come back to the same initial temperature. So you need to pay attention to some of these characteristics, similar to what we do in thermal processing. Next slide, please. So when you apply pressure, it also produces some temperature increase, and this temperature increase you need to consider. So normally, when you apply pressure, you at room temperature, it produces about 3 Celsius per 100 megapascal. If you do that process at 0 Celsius, it increases the 1 Celsius per 100 megapascal. If you start with 70-degree initial temperature, which is shown in the blue line, it's going to create about 5 Celsius per 100 megapascal. If you look at carbohydrates, protein, they have similar heat of compression like water. On the other hand, fats and oil, because of their molecular structure is different, they are going to have 8 Celsius per 100 megapascal. So you need to consider some of these things, particularly when you want to sterilize food with combined pressure and temperature. Next slide, please. So this slide just shows the temperature history when you do the ultra shear technology. Remember, ultra shear technology use both thermal and non-thermal. So in this case, you have the dark lines, which shows the pressure pulse. So in this case, the pressure is applied to 300 megapascal. And in the bottom, you see that light shaded is the temperature within the pressure chamber. So that's the temperature of the fluid within the pressure chamber. If you look at the top, you have the temperature at the exit of the shear bar. So that's the temperature that shaded line. So it just shows that different components going to have different temperature. You kind of monitor the temperature and pressure, and ultimately help to establish your microbiological safety as well as the nutritional quality. Next slide, please. And here I'm just showing an example. The heat of compression is 3 degrees Celsius per 100 megapascal in the case of high pressure processing. On the other hand, when you do ultra shear technology, it's about 18 Celsius per 100 megapascal. So there's a significant thermal effect happening during high pressure homogenization or ultra shear technology. Next slide, please. So that brings to an interesting thing. When you have microorganisms, when you have chemical reactions, when you have nutrients, they are sensitive to both temperature and pressure, or they may be sensitive to UV light as well as temperature, and so on. So you need to consider combining pressure and heat, or combining non-thermal agent and thermal. Are they going to be synergistic or antagonistic? On the right side, I just illustrate with the thermal. It's a formation of some chemical marker by heat. You can see that it's processed at 105 Celsius and different times. The marker yield increase with the increasing time by showing that higher elevation for the bar. If you look at the next two slides, next two material, it talks about 700 megapascal 30 Celsius, 350 megapascal 30 Celsius. You can see that these are done at 30 Celsius, so the pressure primarily dominates and the marker yield is suppressed by the high pressure. On the left side, you can see that same thing happens at 350 megapascal, 105 degrees Celsius, 700 megapascal, 105 degrees Celsius. When you increase the temperature, the temperature try to increase the marker yield, pressure is trying to suppress the marker yield. As a result, you're going to have increased marker yield but less than heat processing. So the same way when you high pressure process food at the function of temperature, the microbial reactions may be influenced by both temperature and pressure, or UV and many other reactions. We will see some examples later on, but you need to keep that in mind when you are designing your process. Next slide, please. So when you look at the microbiological safety, what are the general criteria you need to do? First, you need to know what's the most resistant pathogen organism of public concern and what reduction is needed, and how the food matrix is going to help the survival of the pathogen, and then you need to validate the efficacy. In other words, uh, don't just look at thermal processing literature and then just simply adapt it, because the mechanism of action, different non-thermal technologies different. So you need to make sure that the concepts can be applicable for that non-thermal technology. Next slide, please. So you kind of look at various non-thermal technologies. So we talked about a number of non-thermal technologies. Most of them are quite effective in inactivating vegetative bacteria, yeast, mold, and things like that. On the other hand, spores are highly resistant. They cannot be inactivated by, say, high pressure, electric field, or UV by itself alone. So oftentimes you have to combine with heat so that you can able to have a combination or hurdle technology for that to be effective. A lot of times, since heat is involved, the Clostridium botulinum seems to be most resistant pathogen for some of these sterilization technologies. Next slide, please. The other thing you need to consider is the strain variability. So, for example, if you look at Listeria monocytogenes, there are hundreds and hundreds of different strains available. A study was conducted by treating 100 different strains of Listeria monocytogenes, 350 megapascal, 10 minutes. And the results are interesting. If you look at the center, maybe about 25 strains were achieved 3 log reduction. And if you look at the other extreme, 6.75 logs were achieved for maybe 1 or 2 strains. And if you look at the left on the other extreme, you had highly survived spores, maybe 0 or 0.75 log reduction. Now, which strain do you choose? If you choose the center 3 strain, then you have a chance of bacterial survival. And if you use the strain on the right, 6.75 log reduction, you may say high pressure processing never commercially possible. So oftentimes you need to look at your local farms and local, like a state or region where you are working, and you need to identify what Listeria strains cause outbreak over the time, and you need to conduct validation studies using those strains. Because one of the common mistakes people do is they look at the literature and they may do use a strain reported in US or Europe, but that strain may not be a strain in, for example, in South America or Latin America and so on. So you need to kind of focus your local strains and make sure that these are processed and adequately addressed. Next slide, please. So what are the critical process parameters we need to consider? You need to consider high pressure, electric field, UV, and so on. You need to consider the temperature. You need to consider the treatment time. And then in addition to that, the acidity level can influence the microbiological safety. The water activity can influence. The composition also influence your microbiological safety. Next slide, please. Now, you can be able to pasteurize various products using various non-thermal technologies. In fact, I think a lot of the high-pressure pasteurized products are available. In the early days in the US FDA, primarily limited pasteurization to heat treatment. Now they allow pasteurization done with non-thermal technologies using, for example, high pressure, pulse electric field, UV, and so on. On the other hand, the commercial sterilization, it is still a combination processes. FDA like to see you provide adequate spore inactivation using combination of pressure and heat. So for example, pressure-assisted thermal processing, which combine both high pressure and heat to sterilize food. And they issued letter of no objection for a mashed potato product as well as a seafood product. Next slide, please. This slide just to show you how the resistance of the Listeria monocytogenes, the Salmonella, Aspergillus flavor, Bacillus subtilis spores as a function of thermal sonication and the thermal treatment. So if you look at the top portion of each curve, so for example, the one in A, you have the D values reported for heat treatment. When you use the thermal sonication, it reduces the temperature required and make the process much more effective. So when you use different non-thermal technologies, you will see the similar approach. When you combine heat and non-thermal, you're going to reduce the intensity of heat, but still make it microbiologically safe. Next slide, please. This slide just to show the similar thing, but using high pressure. You can see that 0.1 megapascal on the first left slide, 0.1 megapascal. You have thermal only. When you add heat, pressure, 500 megapascal for purple one, and then the yellow 600 megapascal, and then the blue 700 megapascal. You're going to have more inactivation by altering your D values. The interesting thing is if you look at 120 Celsius, the pressure becomes less and less effective and temperature becomes more dominant factor. And the right side graph, it shows the same thing as a function of pressure, but you have for different heat conditions. And in the table below, you have the Z values, the temperature sensitivity coefficients for different temperatures, as well as the different pressures are given. Next slide, please. This slide just to show what happens when you combine pressure, temperature, and heat, temperature, pressure, and shear process in the case of ultra shear technology or high pressure homogenization. The first slide is for 0 holding time. The second slide is 5 minutes holding time. So in general, what you learn from this slide, it's a busy slide, that higher the temperature, higher the pressure, longer the holding time, you're going to have more inactivation. However, the shear forces have less effect on the inactivation of the bacterial spores. Next slide, please. This slide just shows the integrated process lethality model. So when you have used pressure, you have temperature, uh, various lethal agents, oftentimes you have to integrate them so that you know what the combined effect. So you need to develop mathematical model that consider the effect of pressure, temperature, shear, and various lethal agents. To illustrate this concept, the first slide on the top shows the lethality effect of both pressure and temperature. This is done at temperature at 105 degrees, 103 Celsius, and you can see that the effect is kind of very limited. You have very less thermal effect, and you probably don't have much pressure effect. As a result, the integrated lethality is primarily restricted. So the the purple line is thermal, the green line is due to the pressure thermal effect. If you look at the second slide, you're going to have done at 600 megapascal, 116 Celsius, 5 minutes. And you can see the green line is the pressure thermal effect. The purple line is thermal only effect. You can see that as you increase the temperature, the pressure thermal and thermal become similar. So that means you have a window where both pressure and temperature have a lethal effect. Above a certain window, you only have thermal effect, and there's no efficacy due to high pressure treatment. So you need to consider this when you're developing the process. Next slide, please. You also need to consider the holding time. So for example, on the right, you have a green bee processing. You can see that you have certain time and temperature required. So for example, if you look at 105 degrees Celsius, you probably need at least maybe, so he's showing on the egg patty, you at least need about 18 minutes in the top red to inactivate bacteria at 105 degrees Celsius. If you move to the temperature to 115 Celsius, you can see that the temperature reduced, the time reduced to 6 minutes. So it's kind of function of temperature and pressure, but you also need to consider the holding time. And you can develop similar graphs for green pea and a number of other food matrices. Next slide, please. A lot of times, the university research conduct research in the lab scale equipment, but you need to make sure the results can be scaled up. And for that, you need to use appropriate surrogate organisms. There are only limited number of studies available to show the surrogate organism for scale-up studies because a lot of the researchers focused on pathogens, but limited studies on surrogate. And you also need to know what are critical process parameters. And when you have a thermal process deviation, so for example, when you have high pressure processing, what if you target 600 megapascal, but not enough pressure is built? How do you ensure you have a safe process? You also need to consider the cleaning, hygienic design, sanitation of the equipment, and you need to make sure that the equipment is made from surfaces which are approved for food contact surfaces. So you also need to consider migration of compounds from equipment surfaces. So for example, when you treat pulse electric field processing, if you do not use the proper electrode, you may result in, due to electrolysis, certain electrode materials migrate into the food, which may exceed certain threshold. So you need to consider some of those factors. Next slide, please. And packaging also play an important role. So you need to make sure that, especially when you are doing batch processing, you need to make sure that the pressure, your electric field, how that affect the permeability properties of your packaging material. Next slide, please. So this slide just shows different packaging material: nylon, EVOH, EVA, nylon, EVA, metallized polyester on oxygen permeability. What you see that certain packaging material like metallized polyester, nylon, and so on, their barrier properties are significantly affected compared to nylon, EVH, EVA, where the treatment doesn't affect the barrier properties. So you need to kind of pay attention because these food materials have a longer shelf life. So if the barrier property change, that can affect the shelf life of your packaging material. Next slide, please. Next, we are going to talk about some of the preserving the health promoting compounds. And so there's a lot of opportunities here because, for example, in the case of high pressure, you may have some chemical conversions can happen. So, for example, conversion of glucosinolate into isothiolate so that you can be able to utilize this as a healthy sprout, or you can improve the bioaccessibility of tomato in lycopene. So there's a lot of those things also needs to be medically verified so that we can able to substantiate the health benefits. So right now, most of the science research is limited to food science and technology. However, there's a need cooperation between food science and medical science disciplines so that we can able to demonstrate the healthy benefits. Next slide, please. So this slide just shows how high pressure affects the ascorbic acid. The first slide on the left, just heat treatment alone. The one on the right in the top just shows that pressure is preserving ascorbic acid. The one at the bottom shows that when you add high pressure with heat, you're going to have a degradation of ascorbic acid because the heat is not good, whereas pressure is protecting the ascorbic acid. Next slide, please. This is just shows that when you have different juices, they can form furon, especially when you expose to the thermal treatment. That's shown here with the red bar. Different pineapple, watermelon, cantaloupe, all those showing different levels of furon formation. On the other hand, the HPP, which is pasteurization, shown in the black, you can see that it's below the detection limit, whereas the pressure-assisted thermal processing, that just shows the green, you have some formation of the furon happening under those conditions. Next slide, please. Most of the non-thermal technologies are not very effective in terms of inactivating enzymes. So the best approach is maybe thermally pasteurize them before, or thermally blanch them before you preserve them with, for example, high pressure pasteurization. Next slide, please. There's also an interest to understand how different non-thermal technologies impact different nutrients. So for example, we know non-thermal technologies have a different impact on, for example, salmonella, E. coli, listeria. The question is, are they similar effect on different nutrients? So I think so there are limited studies have been done. So recently we have done some studies. Next slide, please. Where we looked at the beetroot and looked at different metabolites in the beetroot. And you can see that we were treating them with the thermal processing shown with the red, and then we also treated them with the ultra shear technology, high pressure processing, and different biomarkers were differently influenced. So these type of studies are limited. Some of the metabolic analysis are limited, but the more we understand this, then we can able to identify how different non-thermal technologies not only make the food safe, but also preserve the nutrients, and we can able to really understand its health benefits as well as the microbiological safety. Next slide, please. So when you look at the balance between the food safety and the nutritional, it's also worth emphasize you have to make sure the food safety is the number one priority, but you also need to consider quality. If you make a mistake in this example, make a mistake, you're kind of trying to take too much risk, you can fall into the sea. That's a major thing. On the other hand, if you act very conservatively in terms of food safety, you're going to have a significant quality deterioration. So as a result, you need to find a way to balance ensuring safety, but without compromising the food quality. This is a challenge for the coming years so that we have a better process that preserve the nutrients without compromising the safety. Next slide, please. So here, this same concept is explained. I think when the PDF was generated, the curve probably didn't show, but basically it just shows that when you have irradiation treatment, there's an acceptable range where you can able to make sure you inactivate the um, target pathogen, that's shown by the D value, but you also have uh, reduce the dose response for lipid oxidation, color change, aroma, and so on and so forth. So you have to kind of balance those so you can able to kill the E. coli, but without compromising some of the quality deterioration. Next slide, please. So when you have a new processing technology, you have to think new products because a lot of times the novel processing technologies, these are tend to be expensive. So just because you have new technology equipment and you treat water, you may not see any benefit. On the other hand, when you create unique product like guacamole or many other products which didn't exist in the market but satisfy the consumer demand for health and wellness, you probably going to have more opportunity for successful in the marketplace. Next, please. Next slide, please. Next couple of slides, we will talk about the sustainability because it's also important. And generally speaking, the non-thermal technologies like high pressure and PEF have relatively similar or better in terms of um, energy use, and but they also have nearly zero carbon emissions and global warming potential. Next slide, please. And this slide compares the impact of high pressure processing heat on an orange juice. Again, this is a busy slide, but the basic message is that non-thermal technologies such as high pressure PEF, they have less impact on the environmental impact because they have less heat use, and as a result, they relatively better in terms of preserving the environment. And um, so I think that basically this message. But this is just a one study. Only limited studies available. We need more of such sustainability studies comparing different processing technologies. Next slide, please. So when you switch to non-thermal technologies, they are powered by electricity. So that means you have more flexibility. You don't need to produce steam, which causes environmental impact. You can probably use, for example, nuclear power, solar power, or energy, windmill, and so on. And so that's something there. Another thing you need to consider is developing biodegradable packaging. Right now, most of the non-thermal processing technologies use plastic packages. That's also an environmental concern. The nanoplastic, microplastics in the environment is a major concern. So there's a need for developing biodegradable packaging material so that they can be truly sustainable and environmental friendly. Next slide, please. Ultimately, when you develop these technologies, consumer acceptance is important, and consumers may not understand what are the benefits of the non-thermal technologies. So, for example, a panel of consumers talked about different technologies, and when you talked about, say, some of the electrical-based technologies, they worried. They said, "Why you need to pass electricity through my food?" I kind of scared about it. On the other hand, when you talk about some of the pressure-based technologies, the consumers probably did not understand the level of pressure used in the high-pressure technology. They said, "My grandma used pressure cooker, so that nothing with new this. I'm familiar with this technology." So the term pressure, they felt comfortable, but they did not realize that the magnitude of pressure. When you further explain that these technologies can extend the shelf life 90 days, 120 days, then they said, "What did you do to my food? It's natural. I expect my food to spoil in the refrigerator within 1 or 2 weeks, but you are saying it can last longer." So they cannot understand why the high pressure technology extends the shelf life. So they kind of have a limited scientific appreciation, and it's important for the food scientists and engineers to communicate the benefits and risk of the novel processing technologies so that the consumer's acceptance is there. The more the transparent and communicate the benefits, then it's probably going to be accepted well by the consumers. Next slide, please. We also need to pay attention to the limitations of the non-thermal technologies. A lot of the non-thermal technologies, they are not effective in inactivating spores and water activity. So when the water activity is below a certain value, non-thermal technologies like heat is also not effective. You have air packets, that's going to diminish the effect of high pressure PEF. When you have shadowing, light-based technologies may not work very well. And many of the non-thermal technologies tend to have higher equipment costs because they are more prototype, so the cost is higher. More industrial adaptation will bring the cost down. We also need to have more studies on the health benefits of non-thermal technologies. Limited studies looked at the heavy metals, pesticides, and also the micro nanoplastics and so on. So these are not treated by non-thermal technologies, so we need to make sure we pay attention to some of these technology limitations. Next slide, please. We also need to have a workforce development because when you have non-thermal technologies, we need a trained workforce, both at the processor level as well as the various equipment providers, as well as the regulators and so on, so that we can able to develop an ecosystem which develops the industrial adaptation of this. So the universities play a great role. University industry cooperation is going to be critical for developing the workforce, as well as help to train the current workforce. Next slide, please. So this just to show you that you can interact with the industry through power plant demonstration, short courses, webinars like this, as well as some of the food processor fact sheets and so on. Next, please. So in summary, non-thermal technologies, you can think about them each as a tool. You don't want to argue this technology is better than the other technology and so on and so forth. Think about them as a tool. You may have different applications and you have different tools, which may be effective, not effective, and you need to understand that and utilize them properly. And right now, there's a lot of opportunity for industrial adaptation happening right now. But you need to pay attention to the fundamentals so that you can able to understand the impact of non-thermal agents against different food components so that you can create novel food products. So it's important to understand the unique advantages and limitations. Ultimately, consumers are interested in food. They probably don't understand the technology or the science behind it. So we need to make sure that we educate the consumers and provide them with the right formulated food which are demanded by the consumers. With this, I conclude my presentation. Happy to answer any questions. And these are some of the reading materials you may use.
Thank you very much, Bala. We appreciate your dissertation. We have a few questions. The first one is a two-part. Are you aware of any study that has evaluated migration of compounds from plastic to the food products during HPP processing?
Yes, we have done some studies. I have done some studies around 2000. Um, the interesting thing is migration of plastic into the food in high pressure processing is one of the first thing the researchers looked at. It turns out that when you apply high pressure, it compresses the plastic and then plastic become more rigid so that it doesn't allow migration of any of the compounds. And it also doesn't allow any food material transfer into the pressure transfer fluid. So it doesn't allow the pressure transfer fluid come through the plastic or plastic material come into the food. The vice versa also true. So as a result, the U.S. Food and Drug Administration do not have that question anymore.
Okay, so thank you very much. Follow up to that one. What about, and I think you mentioned this on your talk about biodegradable plastics. Is there an interaction, either positive or negative? For example, in HPP processing, if the material, the food container is of a biodegradable nature?
Right, that's a good question. Right now, this is more in the research stage, probably not yet commercially available. So there are companies trying to incorporate some of the um, plant-based materials into the plastic so that they have a biodegradable material. But whether or not they are subject to high pressure, withstand the pressure, I think probably it's going to take some time before commercially applied.
Okay, thank
So
you very
it's
much.
probably we do not know the full answers.
Okay, thank you. You mentioned carbon footprint, you mentioned energy consumption, water consumption. So you've covered this, but do you have a general idea of about the overall cost of using a non-thermal processing technology when compared to a more traditional thermal processing? Now, we cannot compare apples to apples. But overall, some people perceive, for example, that non-thermal might be more expensive, the final product, because there's a premium in terms of quality and nutrition. Also, the investment in technology is larger. But do you have like an overall estimate on that relationship in terms of cost? What is going to cost the consumer?
Right. I think that's a great question. So the non-thermal technologies, I think, first introduced in the US around 1997. So it's almost 3 decades. So relatively speaking, at the time the equipments are relatively less limited companies made the equipment, so the cost of equipment are very high. So, for example, a 200-liter vessel used to cost maybe $15 million. Now, those vessels cost maybe 1 or 2 million. So, the cost of the equipment over the last 20, 30 years came down because you have more companies make the equipment and they also have more demand and supply. So, as a result, the cost is coming down. So if you look at the same thing with the unit basis cost. Non-thermal technology used to probably maybe per pound of making uh, juice or any food product, it may be 5 cents more compared to thermally pasteurized product. But today, this became fraction of a penny or 1 or 2 pennies because the cost came down, because the equipment cost reduced, and then they also know how to package and efficiently use their systems and so on. So the bottom line is still today non-thermal technologies are slightly more expensive or similar compared to thermally pasteurized, but that cost comparison going to probably less and less important with more companies adapting this technology. So right now we are just in the middle, right? So I can also give you another example. In the early days of canning, when Napoleon was introduced canning, the cans were like one soldier probably can purchase 4 cans from 1 month's salary. Today, you don't think about purchasing cans because they're inexpensive. The reason is over the last 200 years, the cans become more commercially adapted, so the cost significantly came down. So the same thing probably happening. We are in the early days of non-thermal industrial adaptation. With more industrial adaptation, the cost is expected to come down. So as a result, you need to pay attention to premium products today so the consumer don't mind paying for it.
Mhm.
You don't want to just process a commodity product and expect consumer to pay because consumer may not understand the quality benefits until they consume the product.
Okay, thank you very much. Are you aware of any study or have you conducted research concerning the impact of non-thermal technologies on agrochemicals, pesticides, herbicides, fertilizers, and so on?
As I was telling earlier, I think those studies are limited. Right now, I think there are some studies start coming out on pesticides and things like that. But I think like I think there are a lot of the agriculture raw products have microplastics and other things, and non-thermal technology may not be effective. So that's something we need to consider, keep into account.
Okay, just two more questions. From your research institution and your research program, do you carry out any extension efforts to educate consumers on the benefits, impacts, and so on of these novel technologies?
So we don't do so. So I'm an engineer by training. So we per se do not have education directly talking with consumers, but we participate in the some of the activities. So, for example, in California, someone was conducting consumer focus groups. So we were helping them to ask the right questions to consumers. The same way, when we conduct research, we collaborate with our consumer scientists or sensory scientists, then have them ask the consumers. So while I do not directly interact with the consumers, we work sensory scientists or things like that, so that we understand how consumers react to some of these new technology development.
Okay. And then final question. This is my question. It might not be a technical one. It might be just to get your opinion. So I think you would agree that if we can figure out a non-thermal processing technology with lethal effect on spores would be like finding a holy grail, or the company or person who would come up with that would be very successful. Do you think that we are going to be seeing that in the next, I don't know, maybe decades or century of finally figuring out how to do that efficiently, uh, with concise reproducible results in the food industry?
Yes, this is a topic of great interest to us. We are also doing a lot of work in this area, but we are not there yet. But I think with the advances in the technology as well as the underlying analytical tools, we will have a better insight, and it's a matter of time we will figure this out. So it's probably not going to happen next year, but it may probably in 5 to 10 years. I think it's likely to happen.
Thank you very much, sir. So we don't have any further questions, and we don't want to take too much of your time. So I appreciate your collaboration today. Public is very happy with your presentation. We also appreciate your answers to our many questions, and we hope to be able to see you in some forum in the future, either through these tools, webinars, and virtual talks, or maybe in Costa Rica in a seminar, in a conference, in a congress in the next few months or years. So thank you very much,
Sure.
Dr. Morales of Romania.
Sure. Thank you very much for the invitation. Happy to be part of the effort and happy to continue interacting with your group. And if there are questions, I'm happy to answer them by email as well. Thank you very
Thank
much.
you. Thank you very much.
Thank you, Professor Bala, and congratulations for your talk. Thank you, Professor Oscar, for lead this Q&A session. And I'm with Professor Oscar. I will be happy to join and to meet you here in Costa Rica. Maybe next year, we are thinking about it. So thank you very much again. Bueno, les felicitamos a todos, al profesor Bala por estar con nosotros el día de hoy y por su maravillosa conferencia. Y bueno, siempre queremos invitarles a nuestras próximas actividades. En términos de inocuidad, vamos a tener al doctor Joseph Baumert hablándonos de alergenos, sobre qué es lo nuevo que hay en este tema relacionado con inocuidad. Y también pues vamos a tener otro webinar el 28 de noviembre sobre estrategias para enfrentar los desafíos y mejorar la calidad de la dieta en Latinoamérica, con varias expositoras de varios países, así que esperamos que nos puedan acompañar. Les recordamos también que en enero tendremos nuestro próximo curso denominado Práctica Basada en Evidencia en Nutrición y Alimentos, y que esperamos pues que también nos acompañen, se registren y puedan participar. Toda la información está en nuestra página web. Una vez más, les agradecemos a todos, les esperamos también en nuestras redes sociales, donde siempre ponemos toda nuestra información, y pronto podrán ver este video también en nuestro canal de ILSI YouTube. Así que thank you very much again, Professor Bala and Professor Oscar. Happy holidays for you, Professor Bala, too. And well, we will be happy to meet you, I hope, in Costa Rica next days. Thank you very much.
Thank you. Bye-bye.
Gracias, muchas gracias, Profesor Oscar.
Buen día, gracias a ustedes, que pasen buen día.
Gracias, profesor.